Hello, my name is Kathleen Coleman, and today I'm going to be discussing my results from the Physics 2211 Lab 1, which is about constant velocity motion. So the purpose of this experiment was to investigate motion of an object that is moving in the same speed and the same direction. The big ideas that you should understand for this are Newton's first law, which basically says that if an object is at rest, it's going to stay at rest unless acted upon by an outside force. And if an object is in motion, it will stay in motion unless acted upon by an outside force. Newton's second law is that the final velocity equals the initial velocity plus the net force divided by the mass times the change in time. And the position update formula is that the final position equals the initial position plus velocity times change in time. Now, the main result from this is that the computational model, you can see, is a fairly good model of the experiment, but as time goes on, it does get worse because the errors kind of compound. And then I also included there a free body diagram with for the ball. In this case, the system is going to be the ball, and the surroundings are the table, the air, the earth, and anything else. So we can see that the normal force upward from the table cancels out the weight force from the earth, and so that's how we get ourselves into a net zero force situation. There's the video of the ball rolling. You can see the points I marked as the center in each frame. I'll play that one more time. And you can see there already that we have our position versus time graph has a positive slope. And this is how I marked my axes. I made the origin the center of the ball in the first frame I started with, and so as it rolls to the right, it has a positive velocity in the x direction. And here is the code that I edited to reflect my situation. So I edited the initial position to be 0.001167 in the x direction, and then I used that position and then the next position with the change in time to find the initial velocity, which ended up being 1.16645 in the positive x direction. I also changed the while loop to make it so that the end condition was t is less than 0.833 because that's when my video ends. I changed fnet to be 0 because that reflects a constant velocity situation, and then I also changed the ball velocity update formula to reflect Newton's second law and the ball position update formula to reflect the position update formula. As for the model versus the observations, like I said earlier, it's a fairly good model, but as time goes on, it gets worse because in real life, we have the friction force slowing the ball down, and in the experiment, we don't. And also some assumptions, were that there's no friction and no air resistance, which is obviously not true to real life. And some additional possible sources of error are human error in selecting the middle of the ball in each frame, plus the ball could have swerved and had, a velocity in the z direction as well. Now to address some important questions. What if the axes were flipped? Well, the situation would be pretty similar, except the position versus time graph would be reflected about the x-axis, so it would have a negative slope. Also, is it possible for you to say how many pushes and pulls are added together to give zero net force in the case that you observed? No, it's not possible to say that. You just know that it's zero net force. You don't know what happened up, down, left, right, diagonal. You don't know what happened. You don't know the intermediate steps. All you know is that it ended up being net zero. And that's the end of my explanation on this lab. I hope you enjoyed.